Good morning, Eastview Scholars. Welcome to this edition of Sharp Shorts, where we are going to talk about water. I open with a little scene from the Sweet Corn Blues Fest in Normal, Illinois, where there's right in front of the stage or where the audience sits and stuff like that is a beautiful kind of fountain area and stuff, just because it's pretty cool looking. Anyhow, today's discussion really is about water, which in biology is the key essential molecule. It's so simple and yet it's so essential to life. It is, as we have noted here, the biological medium on the planet here. This is the thing that keeps life going. All organisms require water more than any other substance. It is absolutely key in most metabolic reactions. When we talk about organic molecules and the formation of proteins and stuff, you're going to see that they work often in producing water in a dehydration synthesis reaction. Most cells are surrounded by water, cells themselves. It is the abundant main reason the earth is habitable. So what is so special about water? Well, it's its structure. It's its structure. It is a polar molecule, as you know. Here we have these polar covalent bonds right here between the oxygen and the hydrogen. And if you remember your chemistry and your electronegativity, oxygen is much more electronegative than the hydrogen, so as they're sharing their two electrons here, those electrons are drawn much more into the orbital of the oxygen than it is the hydrogen, creating a dipole moment where the oxygen will have a slightly negative dipole moment and the hydrogen will have a slightly positive end to it. Okay? That gives it its polarity. What really works with oxygen is the hydrogen bonding there, which we see right here, because of, and again I'll draw the negative dipole right here, because of the attraction between this positive and negative, you create a small weak hydrogen bond, but weak being a somewhat relative term. These bonds really only last in water, but it gives it its property that is different than other liquids in the structure that it gives. It is a weak bond. They last trillionths of a second, barely, but they're constantly breaking and reforming with other water molecules around them. And so therefore at any given moment, really most of water molecules are bonded together. Okay? And so other than being the biological medium for life, other than being the really the only common substance that you see in all phases, liquid, solid, and gas phase, as instrumental points in our atmosphere and our planet, it gives that liquid much more structure than any other, and that leads to essentially what are called the emergent properties of water. Okay, so here we go. As we said, hydrogen bonds in liquid water last only for a few trillionths of a second, but as soon as they break, they reform. So water is actually more structured than most, and here are those emergent properties, and we're going to look at them all. The ability to moderate temperature. Think of chemistry and the high specific heat that water has, and we will discuss how that affects living organisms. It is one of the few substances that actually expands upon freezing. The hydrogen bonds actually kind of keep things at arm's length in a sense, and so it floats. The cohesive behavior leads to discussions of cohesion, adhesion, and surface tension, which are very important in the biological world. And as you probably remember from chemistry, it is very versatile. It is the best solvent. There is no one universal solvent that will dissolve everything, but the one solvent that does dissolve the most stuff is water. And as we have discussed in chemistry and stuff, that is because of its polarity, and most substances are polar, it works very well. Obviously, solubility has degrees with different chemicals and everything else, but water is the key to that. All right, so let's look at these properties, these emergent properties that make water the most essential molecule for life. Okay. The first we're going to talk about here, this is where a good example of where we look at cohesion and adhesion. Okay. And cohesion just means this, that bonding, that hydrogen bonding, holding these oxygen and hydrogen, these opposing things together. Pretend, let's assume this is one of those big redwoods in California that are 8 billion feet high. And of course, for the tree, the water is absorbed, it flows up in the leaves and stuff where the water is needed during photosynthesis to help in the creation of the food substances and stuff that the tree needs to survive. And then the water transpires out of the leaves. Well, as that leaves, it does a couple things, which we'll talk about next with the evaporative cooling and the high specific heat. For the cohesion angle, you can see that these things are kind of pulling. So as these molecules leave and evaporate off, essentially before that hydrogen bond breaks, it is essentially pulling those molecules up. And so that cohesion draws them up against gravity and allows them to work against gravity to pull the water up to the high parts of the tree and up to the leaves. The other thing here, and here you see a picture, these are the water conducting tissues of the tree. The other thing is that polarity allows, you can see here a little adhesion bond to the sides of the tissue. And so if you remember measuring any water in chemistry and stuff, you would get that meniscus, that bending, that surface, that's adhesion. As you get that kind of bubble that pulls up the sides, that's an adhesion force. That also allows for the water to be pulled up along with the cohesion up the tree. Okay? And that's a very strong property of water. In conjunction with that here we got a spider running across the surface of the water. That hydrogen bonding really holds those molecules together. And yes, it is a weak bond, but weak and relative is what it needs to do. So it is much more difficult to break the surface of water than it is in most liquids, which leads to many things besides the cohesion and adhesion and stuff that goes with trees. You've got animals that can then use the surface of the water and all sorts of other properties that go with the surface tension. All right, here we go. Let's talk chemistry. We know that water from chemistry has a high specific heat. It can just absorb and release large amounts of energy. That's why it's used as a cooling and a heating process in many things. And here you can see this example of the difference of land and ocean. And I've got another one here. You can see how that high specific heat, here is an August day, essentially on the coast of California, you have this large body of water absorbing all that energy, as opposed to land here, that has no, it's a low specific heat. It heats up fast. It can't absorb without changing the temperature much on that land. And you can see from the coastal region out to the land region the great difference in temperature. This absorption and maintenance of a constant temperature because of the high specific heat of water keeps the coastal areas cooler than the desert area. Okay, so that's one of the things about the high specific heat. We were talking about the trees and how they transpire and the water leaves from that. This is like you sweating. This is I guess you could call it plant sweat. But evaporative cooling, as these things are leaving, as they are evaporating off the leaf, thinking back to, remember, temperature is the average speed of the molecules, and as that average speed increases, you change phases. those water molecules that are leaving, that are evaporating off as a gas, are taking the highest energy molecules away, which means that the ones left over have to be of a lower temperature. Therefore, that is a temperature control, a maintenance of temperature for plants and for us. That's what sweating does for us, that evaporative cooling. On a very humid day, it feels worse just because you're not losing that sweat. It's not leaving your body as quickly. You're maintaining those high energy molecules on your body, and unless they evaporate, it's going to feel hotter. That's why they've now gone to real feel on all the weather forecasts and everything. Same thing for the plants. As those high energy molecules leave, that evaporative cooling will allow the plant to maintain a lower temperature and not crank up in heat. Okay. Now, density-wise, here we have ice. Here's liquid water. Nice arrow there, Mr. Sharp. Here's the liquid water. You can see the hydrogen bonding and constantly breaking and reforming and having the liquid stuff. But again, water is one of the very few substances that actually becomes less dense, and ice floats on water. And part of that is as things are slowing down. To about 4 degrees, water acts like any other liquid. From 0 to 4 degrees in a Celsius scale. Then it starts altering from other liquids, really because these hydrogen bonds, then they're going so slowly, you can't really break the hydrogen bonds. And so those hydrogen bonds essentially keep the molecules from condensing more into the solid form. They keep things, basically it's, hi, you're at an arm's length, this is as close as you're going to get to me. That makes ice more dense, less dense than the water, and allows it to float. My question for you to think about is, how does ice floating, how does that ability help biological systems, the living things? What benefits do living things get from that? And so I'll leave that question to you. The last emergent property that we're going to talk about is its versatility as a solvent. It is the most versatile solvent that we have. The polarity and that breaking and reforming of bonds allows it to work from the inside out. Here we have, basically this is sodium chloride. So there's your sodium, there's your little sodium molecules, okay, which we know are positive ions. There's our chlorine molecules, which we know are anions. Of course, they have an ionic bond. It's very easy because of the polarity. And what happens as these things dissolve is once you start breaking out from the outside in, the sodium and the chlorine molecules, they get surrounded with with the hydrogen bonding by a hydration shell, which essentially keeps it away from the other ions in solution, keeping it dissolved. And it will slowly work to, relative slowly, depending on the substance, to dissolve that substance. And because it is essentially the greatest solvent in the world, that leads to the versatility. You think back to your chemistry and what that does for acids and bases and its use as a solvent. It's all based on those hydrogen bonds and the polarity and the uniqueness that it does for water. So a very simple molecule, just 2 hydrogens, 1 oxygen in a big V shape, kind of looks like Mickey Mouse if you want to think about that. Okay, but its polarity and it's very, sometimes the most simple things are the greatest things. Its shape, its polarity, its ability to hydrogen bond lead to those 4 emergent properties and lead it to being the medium, the biological medium that we need to, that we believe we and any life outside of our planet would need to survive. Anyhow, that is it for this edition of Sharp Shorts. Scholar Up, Eastview.